to that, to that, to that. P3. Yeah, you guys get the full chunk of this. P3. I told you I'd finish this really quickly because technically you should know all of this already. This is just kind of warming your brain up, getting you used to the way I teach. This is radicals. And technically radicals and exponents are exactly the same, which I'll show you probably not today, but on Tuesday. Radicals. If a squared is equal to b, then we're going to define the square root of b to be equal to a. This is just a definition of what it means to be a square root. Definition of square root. Now, inside of this definition are some subtleties. Subtlety number one. If you take a number and square it, you are guaranteed that that answer is going to be if you take any number and you square it, you are guaranteed that the answer is going to be positive. Guaranteed without a doubt. If you square any number, it's going to be positive. So when you take a squared and you square it, then b is guaranteed to be positive. Or 0. Because a could have been 0. So you are guaranteed that b is positive. Remember, b greater than or equal to 0 means b is positive. Trying to get you used to the language of math. Now, if b is positive, then when I take the square root of b, the answer is going to be positive. Why would it change signs? So this also guarantees that a is positive. This is considered a principal root. Because when you take a square root of a number, like square root of 25, for instance, write that down. Square root of 25. Why do we say that the answer is positive 5? Oh, it's because of the definition. But does it have to be 5? Because if I remember right, the way you learned this in like 7th, 8th grade was, what times what is 25? 5, and that's why the answer is 5. But isn't negative 5 times negative 5 also 25? But then that would say the answer is negative 5. But that's why we have this idea of principal root. We want one answer out of the thing, not 2. Because with calculations, with operations, we want one answer and not any more than that. So that's why we have this thing called a principal root. So if you're dealing with square roots, you have principal roots to work with. Your answers are always going to have to be positive. Okay. So if I have something like this, what's the answer? Great, but x can be anything, which could be positive and or negative, and we want to make sure that this thing is positive all the time. So how do I make it positive all the time? Absolute value. So the answer to this is really the absolute value of x. But a little star by this is the one little fact that most people forget. That if you take the absolute value of a variable squared, you've got to be very, very cautious about the sign of that variable. Oh, and by the way, when you take an absolute value of x, you get a positive part and a negative part. This actually has 2 answers, which is kind of weird, but it does have 2 answers. But we want it to only have 1, so absolute value of that value, 1 answer. Woo-hoo. But later on, we'll talk about 2 of them. Okay. Rules of radicals. Whenever you learn a new number system, there has to be rules associated with it. When you work with whole numbers, you learn how to add, subtract, multiply, and divide them, and they had certain rules about them. When you jumped into integers, all the rules got all messed up and you get confused, you know. Negative plus a positive, you have to worry about which one's bigger and keep that sign, but subtract the numbers and all that fun stuff. So there are rules of radicals you have to follow to write them correctly. Probably the best example would be a fraction. If you write on your test 5 out of 25 or 5 over 25 and you leave it as your final answer, you lose a point. Because 5 over 25 can be reduced. So the same thing happens with radicals. You can't leave things like square root of 8 Or you can't leave things like square root of 25 because the square root of 25 is, it can be simplified. So anytime things can be simplified, you have to. So rule number one, cannot leave a perfect root under a radical. You have to simplify them. You have to break it down into its primal pieces. All right. Number two. I'm trying to remember what law number two is. Well, we can use this rule. Square root of a times the square root of b is the same thing as the square root of ab. One thing you have to remember about equal signs is you can read it left to right and right to left. So the one we're going to use mostly is going in this direction, where we take the a and the b and we separate them. So the square root of ab is the same thing as doing the square root of the first one times the square root of the second one. The problem with that law is people want to do things like this. What's the square root of x squared plus y squared? Most people with xy or x plus y or the absolute value of x plus the absolute value of y, which would be a little bit more proper, but that's the answer. You can't simplify it. What's the difference between x squared plus y squared and a times b? This one is multiplication and this one is addition. For the most part, addition and subtractions don't simplify as nicely as multiplication and division. So try not to think of simplifying pluses unless you really, really are desperate. If it's multiplication, generally it'll separate. If it's addition and subtraction, don't even try to separate them. Under most cases, it doesn't. This also has, the quotient part of it. You can separate the top away from the bottom. Better look at my notes. Make sure I'm hitting all these laws. 1, 2. Yeah. 3. Cannot leave a radical in denominator. Cannot leave a radical in the denominator of a fraction. I'll explain that one in a second. Similarly, 4, you cannot take a radical of a fraction. You just can't do it. Because of number 3. All right. Go back over here. So why can't I leave a radical in a denominator, like, 5 divided by the square root of 2? What's wrong with that? I can type it into my calculator, it'll give me a nice little answer. So why can't I leave a radical in the bottom? Well, it's actually kind of simple. How do you divide 5 by 1.25? Oh, without a calculator. I know how you're all addicted to calculators. So how do you divide 5 by 1.25? Well, you have to do long division. So you go 1.25 goes into 5. What do I have to do with the decimal point? I have to move it over twice here. But if I move it twice here, I have to move it twice here. So this becomes 500 divided by 125. It goes in 4. I think it's 4 times. Yeah, whatever. Quite sure it's 4. Because 4 times 100 is 400. 4 times 25 is 100. So you get 500. All right, so what if I have 5 divided by the square root of 2? Why can't I do that? Well, what's the square root of 2 equal to? Now I need a calculator. What's the square root of 2 equal to? 1 point. I know that much. Oh, calculators.
1.11.2.13.5.6.2.
Why are you stopping?
That's there's no more room left in the calculator.
Oh, there's no more room left on the calculator. Well, how far does it go?
The arrow goes to infinity.
Infinity. All right, dot, dot, dot. Goes into 5. How many times would you have to move over the decimal place? Can you? No. That's why you can't divide by radical, because you cannot move that decimal place over enough times to divide it into the 5.
What if the square root comes out to be a straight number, a whole number?
Well, that falls under number 1.
All right.
You cannot leave a perfect square root under a square root.
I got
So if you have 5 divided by the square root of 4, the best way to write this is 5 over 2. You don't leave that radical at the bottom. One way or the other, it has to go, away.
Disappear, go away.
Let's say rewritten. We're going to learn how to rewrite that so we're not dividing by the square root. The reason you can't have a fraction under a square root falls under the same reasoning. If you have the square root of 1/2, you have to use rule number 2, the second part of it, the fraction one, and you separate it as the square root of 1 over the square root of 2, and the square root of 1 is equal to, oh God, don't you dare type that into a calculator.
Is it 1?
It's 1, boy, over the square root of 2, and then the problem becomes, again, we're dividing by a radical, an infinite decimal, which is impossible. Okay, so that's the reasoning behind the last 2 rules. Now, number 1 is where most people concentrate their effort in simplifying radicals, being able to break them down. Now, there's the book method, and then there's my method. Guess what I hate? The book method. The book method requires you to overthink things. For instance, the book method, I'll keep it simple, square root of 8. The book method says, what is the perfect squared number in 8? Well, it's 4. So you would break this apart into the square root of 4 times 2. Get this radical a little bit longer. And then you would use rule number 2 to separate it. So it becomes square root of 4 times the square root of 2, which is perfectly fine. And then the square root of 4 is 2. So the simplified version is 2 square roots of 2. Or 2 times the square root of 2. That's the book way. The problem with the book way is some numbers you're going to look at and you have no clue what the perfect square is. And there's some numbers that I look at it that I have no clue what the perfect square is. So their method kind of falls apart for those, and you won't be able to simplify. So let's do something like this. No, not that one. This one. For example, the square root of 108 x cubed y to the 5th. Now, I'm looking at 108, and I need to find the perfect square in it. I can't think of one. So, here's my method. What is the smallest number that divides evenly into 108? 2. And it's always going to be asked that way. What is the smallest number that goes into it? Don't just pick a number that goes into it, the smallest one. 2 goes into 108 54 times, right? What's the smallest number that goes into 54?
2.
And? 27. 27. You'll get used to these numbers. What is the smallest number that goes into 27? 3. 3 and 9. What's the smallest number that goes into 9? Of course, is going to be 3 and 3. Now, by definition, to take a square root, you're looking for perfect squares, or 2 factors. 2 factors. So all I have to do is pair up factors. Well, this one has a pair of 2s, and it has a pair of 3s. But when I pull these perfect pairs out, the square root of 25 just became 5, one of the factors. So I'm going to pull out a single factor of 2, and I'm going to pull out a single factor of 3. And 2 times 3 is 6. So the first number I'm going to write down is 6. All right. Now let's get to the variables. X cubed. Well, that means I have 3 factors of x. I need to pair up one of them, pair them up. So I can pair up one x and pull it out, and that leaves behind another x. What operation is that when you take 3 and then you group it into 1 and 1? No, not property.
Uh-oh.
What kind of operation? When you have like, I have 3 people and I have to share $2 with them. Division. So 3 divided by 2 is 1 with a remainder of 1. So it's a little bit of division here. All right, so let's see here. We can pull out a single factor of x. How many of the y's can we pull out? Well, there's 5 of them. And if I group them, you get the, live long and prosper. How many people can do that? You can pull out 2 and leave behind 1. So you get y squared, 2 factors of y, and we're going to leave 1 behind. There's still stuff under the square root, so that becomes max. What's left out of the numbers?
3.
It's always going to be along this diagonal. That's another reason I go for the smallest number. Don't look at the 54, the 27, or the 9. The only number left is
3.
that 3. He's all by himself. And remember, we left 1x behind and 1y. And that would be the simplified version.
Why couldn't you taught me this in the beginning? It's so much easier your way.
I know.
The other way I learned was
I wasn't your teacher, I'm sorry.
I gave up on it.
You gave up on it?
Yeah,
Oh.
I was like, forget it. My grade
Because they
was
made
higher.
you do it the book way.
Probably so.
Figure out what the square root is. Where's that perfect square root? Ooh, clean my board. How much time do I have? One more example. How about, let's keep it simple. This one. Square root of 3xy squared times the square root of 6x. Oh, by the way, there is a mistake in this answer. Do you remember one of my little laws, the square root of x squared is equal to the absolute value of x? Technically, there's supposed to be an absolute value around this x. Technically. Why not the y squared? No, because anytime you square a number, it's guaranteed to be positive, so I don't have to worry about him. But technically, I'm supposed to have the absolute values around the x. To get rid of that confusion for a little while, we're going to make a horrible assumption. This is a bad assumption, and don't you ever use it beyond this little portion. Assume all variables are positive. If you do that, you don't have to worry about the absolute values. But that is a bad assumption because then people start thinking that variables are always going to be positive and they can be negative. If you were taking this online, some of the problems will say, assume the variables are positive and they want the answer without the absolute values. But then other ones, they'll say, what is the simplified version of this? And they're looking for the absolute values. So you've got to be cautious how the wording is. For my class, for my tests in here, all variables are positive for only square roots. For only square roots. All right, so how would I simplify this expression? Well, there's that neat little law that says the square root of A times the square root of B is the same thing as the square root of the product AB.
So is it 18x squared?
Well, you start off with the square root of 3 times 6 is 18.
X squared.
X times x is x squared.
Y squared.
Y squared. Bring it all underneath one roof. And then 18, if you want to do it my method, smallest number that goes into 18 is 2 and 9. And 9 breaks up into 3 and 3. And you group up the pairs, so I'm going to pull out a 3. So 3 goes out front. And then if you have a pair of x's on the inside, it becomes x on the outside. If you have a pair of y's on the inside, it becomes y on the outside. Without that assumption, it's the absolute value of x, y. Either absolute values around each of them or around the entire thing. Square root of what's left behind?
2.
This 2. It's the only thing left behind. And there's your answer. Okay, so homework. And attendance. Let's do attendance first. I'll keep you.
Are you recording this or are you going to record the next class?
Oh no, I recorded this one. We're actually going to do 2 sections today because some of the things that they ask you to do with radicals are actually in P4, which is polynomials, FOILing and distribution and multiplying terms. So what I'm going to do is I'm going to do a little bit of P3, stop when it gets to the polynomial part, switch over to polynomials, teach you at least the multiplication of them, and then jump back into P3 and finish it off. Personally, I think the polynomial chapter should have came first, or the section, and then the radicals, because you're using some ideas out of the polynomials. So let's start with the rest of P3. For instance, another definition. So this is P3 continued. So your notes are going to be a little bit back and forth, but it's not bad. P4 most of you know how to do anyways. So a definition, if a cubed is equal to b, then we're going to define the cube root of b to be equal to a. Now when we did this with square root, we said, you know, if a squared is equal to b, then the square root of b is equal to a. And we were very precise about the values of a and the values of b. They both had to be positive in the case of square root. But in the case of cube root, do both of them have to be positive?
No.
No. Because if you take a number and you cube it, if it starts off negative, your answer is going to be negative. If you start off positive, your answer is going to end up being positive. So here, a and b are just real numbers. Might as well get used to some notation. The double bar R means real numbers. It's a short abbreviation for it. So A and B can be any real number, positive, negative, 0, it really doesn't matter. Okay. So, what is the double bar R? It means real numbers. This is the real numbers.
Oh, okay, you did a double,
Yeah, it's a double bar.
All right.
It just means real numbers. A double bar Z means integers. You get used to weird symbolism in math. All right, so for instance, I think you should know some of these, like the cube root of 27. What do three numbers multiply together to give you 27? 9 times 9 is 81, so that's square
Yeah,
root.
just trying to get 3 times.
Yeah, so it's 3 times 3 times 3, so it pops out as 3. If you have, these are the popular cube roots. The cube root of negative 8. Negative 2. Because negative 2 times negative 2 times negative 2 will give you negative 8. So that's all it means to be a cube root. So let's simplify one. For instance, the cube root of 54 x to the 7th y to the 4th. Cube root of 54 x to the 7th y to the 4th. Now just like with square roots, you're going to break it down using that factor tree, breaking it into prime factors. So what's the smallest number that goes into 54? 2. So it's going to be 2 and 27. Smallest number that goes into 27? 3 and
9.
And of course 9 breaks into 3. Now square roots, you were looking for pairs. Cube roots, you're looking for triplets. I call them triplets, but yeah, 3 of them. And the reason for that is this little number up here. This number up here is called an index. Square roots also have an index. You just don't write it. What's the index of a square root? 2. Because you're dividing things by 2 or finding pairs of numbers. So here, this tells you how many factors you need before you can pull it out as a single factor. So this one says you need 3 factors. So here's a triplet of 3s. So the number that's going to pop out is 3. When you get to the variables, we're going to do the same type of trick. With square roots, we divided by 2. Here, we're going to divide by 3. 3 goes into 7 how many times? Twice. So you're going to get x squared. 3 goes into 4 how many times? 1. So we're going to get a single factor of y. Write down your radical. What's left behind?
2.
This 2.
X.
A single x?
Yeah.
Well, 3 goes into 7 twice with a remainder of 1. So yeah, single x. So 2x and a single y because we took away 3 of them. Is that correct?
Yes.
No?
You forgot the index.
I forgot the index. If you don't put the index in there, this is the square root of 2xy, which is different than the cube root of 2xy. So make sure if it starts with an index, you carry the index all the way through the problem. That's a very common mistake of dropping that off, and it does change the answer a bit. And that's it. Isn't that easy? You're all like, it's like Monday morning. Kind of is. How about higher indexes? For instance, if a to the fourth is equal to b, then we're going to define the fourth root of b to equal a. Not very often that you see a fourth root, but they do crop up. Okay, is there any restriction on b? Is there any restriction on the value of b? If you take a number and multiply it together 4 different times, what are you guaranteed always?
A positive.
A positive number. So right off the bat, b has to be positive. Remember, greater than or equal to 0 reads positive. If b is positive and you take the fourth root of this positive number, then a also has to be positive. So we're back to that idea of we're only going to be dealing with the principal root. Remember, with cube roots, we didn't have that idea because they could be positive and or negative. So when does principal root come out? No.
When the index is even.
When the index is even. So you're always going to have a principal root when the index is even. If the index is odd, you could care less. It could be positive, it could be negative, it could be anything it wants to be. But if the index is even, you got to be careful that the number on the inside and your answer are both positive. In other words, you can't do things like this. Square root of negative 4 is not a real number. It's fake. And you can't have the square root of negative 9 squared to equal negative 9. That just doesn't make any sense. Because when you take the square root of a number, it has to be positive. And there is that property where you take the absolute value, it becomes nothing. So you got to be really careful when you're dealing with even indexes. The number underneath has to be positive. The answer has to be positive. Odd ones, they care less about. All right, what if we define things to be a little bit higher? If a to the n is equal to b, then the nth root of b is going to equal a. This is for any index, any possible index you can think of, as long as n is a whole number. Well, actually, n is greater than or equal to 2 and natural. Has to be a natural number. Can't be a fraction. You can't have the index being like a half. That just doesn't make any sense. Now, the only thing you have to be cautious about is when n is even. That's the only thing you have to be very, very careful about. Okay, so that takes care of all the indexes. Let's do a simplification on a higher index. For instance, (3x) the fourth root of 162 x to the 7th y to the 5th. Now, the higher the index goes, the more you need to group together. So I don't usually go higher than 4, because even if you multiply 5 2's together, the number starts getting a little bit large. 2 to the 5th is 32. And then any other number would just make it ridiculously large. So 4 is usually the highest I go. But you do it exactly the same way. Smallest number that goes into 162. 2 and 81. 81 is not divisible by 2 anymore, but it is divisible by 3. 3 and 27. And 27 is 3 and 9 is 3 and 3. Again, you start seeing these numbers over and over and over again. And you start memorizing which grouping you can do. So how many do I need together here?
4.
All 4 of them. So there's 4 3s, and if there weren't, I couldn't do a darn thing. I'd have to leave the entire number underneath. So I can pull out a 3, but the problem here is there's already a 3 sitting out front. So when I pull the 3 from the inside to the outside, what operation am I using? When it hits the outside? Well, I mean, what operation is straight across this entire problem?
That's true.
This is 3. Yeah, but when you say 3x, what operation? It's 3 times. And then it's times this 4th root of 162 times x to the 7th times y to the 5th. So the entire operation is multiplication. Operation, not property. So the operation straight across is multiplication. So when you pull this 3 out, it's going to have to multiply. So 3 times 3 is 9. All right, now we have this x sitting out here, so we're going to have to be careful. 4 goes into 7 one time, but that x is going to run into that x. So you're going to get
X squared.
2 factors of x, better known as x squared. 4 goes into 5 one time, so that y is going to come out. He has nobody to run into, so he's just a single factor of y. And then the 4th root of
2.
this 2 who's left behind. Now when 4 went into 7 and they pulled out 1, how many were left behind? 3, so that'd be x cubed. And then 4 went into 5 once with a remainder of a single factor of y. And there's your answer. They're about all the same difficulty. There's really nothing harder that I can do about these things. I can put one on the test, see if you know how to do it, but I can't make it more difficult. Because they're all about the same difficulty. All right, let's talk about adding them, which is the same thing as subtracting them. Adding and subtracting is one operation. Okay, so 4 square roots of 3 plus 2 square roots of 2 minus 7 square roots of 3. Can I add anything together here? Yes, what? The 4 square roots of 3 and the 7 square roots of 3. Okay, let's practice our properties. What property allows me to add these two together? Commutative first, you'd have to switch the order. This, of course, is the mental step. This is something you just do in your head and be done with it. How do I add the 4 square root of 3 minus the 7 square root of 3 together?
The base of the square root is the base is the same.
So they're like terms.
Right.
And once you say like terms, what property is that? Commutative only switches order. Associative deals with parentheses, grouping. There's no grouping here.
It's identity.
It is not identity. Because there's no 0, there's no 1. Distributive property. They have something in common, the square root of 3. So what do I do with the square root of 3? Kick it out. So when you kick it out, what's left behind is, well, it's going to be 4 minus 7. Remember, anytime you're doing like terms, it is the distributive property. Remember, I told you to write that down someplace, right? Because it'll show up on my test over and over.
What's that?
Anytime you say to yourself, they have like terms, then that's the distributive property. Anytime you say cancel, it's the inverse identity. Inverse identity. All right, so 4 minus 7 is? So you get negative 3 square roots of 3 plus 2 square roots of 2. Ta-da! Now, I can't add the other two together because they're unlike terms. One's a square root of 3, the other one's a square root of 2. And there's nothing I can kick out because they're not exactly the same. So when we're adding and subtracting, we're looking for things that are kind of polynomial in nature, but I consider like terms. All right, let's make it worse. I mean, that will never be on the test because that's just boring. This is more like what's going to be on the test. I'm starting to get old. I have to hold the paper further and further away from my face. Yeah, I can read it from there. This is two terms. Do they have like terms? Yeah. I mean, there's nothing alike about them. But you can't tell until you simplify the radical. So we have to go through the process of simplifying both of them. So 45 breaks down into
3 and 15.
3 and 15. Make sure you go for the smallest number. Don't break it up into 5 and 9 because then you don't have a nice smooth tree. All right, so you get 3 and 15, which is
3 and 5.
3 and 5. So we're going to pull out
Two.
a 3, but this 3 is going to run into that 3. So we're going to get 9. All right, then we have this x cubed. So 2 goes into 3 once, but that x is going to run into that x, and that makes it x squared. All right, and then we have 2. Remember the index here is 2. 2 goes into 4.
2 times.
So we're going to get 2 factors of y on the outside, and then we can start on what's left. What's left?
5
Well, there's 5,
and x.
and a single factor of x. All the y's are gone. That's like y to the 0, which of course is 1. Minus, all right, now we need to break down 20. So that's 2 and 10, which is 2 and 5. I could pull out a 2, but that 2 is going to run into that 2, making it positive 4. Well, negative 4 here. All right, index of 2 goes into 5 how many times? 2 times, so we're going to get 2 factors of x. Index of 2 goes into y squared how many times?
2.
1
time.
1 time, so we're going to get 1 factor of y on the outside. Square root of what's left behind?
5
This 5
and 1x.
and 1x, because we pulled out all the y's. Now when you look at
Doesn't
them,
that y run into the y on the outside of the radical?
hey, thank you for catching that. When I pulled this y out, he's going to run into that y there, so this is really
Y squared.
y squared. Now are they like terms?
Yes.
Yes. Now they're like terms because they have the same junk in the back end. X squared, y squared, square root of 5x. Both of them have it. So basically I can use a distributive property, pull it away from everything else. What's left is
9x.
9 minus 4, which is 5. And then you just bring the junk back. X squared, y squared, square root of 5x. That's probably the hardest I can make addition and subtraction. And I have all the junk, and you have to worry about things coming out, running into stuff in the front, and then eventually get them to add it together.
I got a question.
Go for it.
Why come the variables don't cancel?
Cancel.
Like when
You're really going to get me mad, aren't you, Willie?
you know not.
Yes, you are. If you have x minus x, they cancel.
Mhm.
But why? Because x minus x is equal to
0.
0, because they're additive identities. And the reason is they both have a 1 sitting in front of it. You factor the x away, so it becomes 1 minus 1 times x. And 1 minus 1 is?
0.
And 0 times x is?
Well, 0.
0. That's why. Now here, when I get rid of the junk, move it off to the side under distributive property, what's left behind is 9 minus 4. You don't change the junk, because that's getting pulled away. It's being kicked out of the house, and it's being safe from the fire. These guys are under the fire. These guys are safe from the fire because they're outside. So don't touch the variables. It's just the coefficients you're really working with. Does that make sense?
Okay.
Okay. These little ideas. That's why the properties are so nice, because they can prove why things are the way they are, and you're not just guessing at it. I'd rather you not guess at all. All right, so that was sum of radicals. Now I need to go to P4 for a little bit. So P3, and finish it off. So back to P3. Negative 2 square roots of 3 times 4 square roots of 6. I'll start off simple. Now, the property that you're constantly going to use with multiplication of radicals is the square root of a times the square root of b is equal to the square root of AB. Now with square roots or even indexes, A and B both have to be positive, but everything else can be anything, doesn't matter. So when I multiply these two things together, what property am I using? There is no distribution here, because there's no plus sign and there's no minus sign. The distribution only works when there's addition or subtraction. This is just positives and negatives. So what property allows me to multiply the 2 and the 4 together? Commutative. Just by reorganizing things, I can write this as negative 2 times 4 times square root of 3 times square root of 6. That's all commutative property. It has nothing to do with distribution. And then negative 2 times 4 is? Negative 8. And the square root of 3 times the square root of 6 by the property up here is square root of 18. If it was under a square root to begin with, it stays there until you simplify it. If it's outside of a square root, leave it outside of the square root. Don't try to mix and match a number and a radical. Is this the final answer? No. Now, 18 is 2 and 9, which is 3 and 3. So I can pull out.
The threes.
And the 3 runs into, and you get negative 24 square roots of
2.
Don't forget him, 2. And there's your final answer. So negative 2 square roots of 3 times 4 square roots of 6 is negative 24 square roots of 2. Kind of cool, huh? All right, let's make it harder. Negative 3 square roots of 5 times 4 minus 2 square roots of 10. Okay. This is like a monomial times a binomial, identical to the polynomial way of doing it. So we're just going to distribute. First times the first times the second. Or outside times the first and outside times the second. So when I do negative 3 square roots of 5 times a positive 4, the only numbers I can multiply together are the negative 3 and the 4, so that's negative 12. Square roots of 5 is just going to kind of hang out. But it's all by the commutative property, reorganizing everything. All right, and then we're going to multiply it to the last one. Negative 3 times negative 2. It's a positive 6. You need to say positive to get the operation. And then square root of 5 times square root of 10.
50.
Square root of 50. But that has nothing to do with the distributive property. You're just getting number to number, radical to radical. All right, am I done? Heck no. 50 breaks down into 2 and 25. And 25, of course, is, so I can pull out a 5. So this becomes negative 12 square root of 5 plus, that 5 is going to run into that 6, 30, square root of 2. And there's your answer. Isn't this easy? Yes, it is. This is nice. Radicals behave like polynomials. So if it works for a polynomial, it'll work for a radical. Okay. How about, well, let's do this one. 2 square roots of 3 minus square root of 5 times 2 square roots of 3 plus the square root of 5. What are these two called? Yeah. Conjugates. They're identical except for one sign. One's a plus and the other one's a minus. So these are considered conjugates. What happens with conjugates is those two middle terms should cancel. So if they don't, you did something wrong. 2 square roots of 3 times 2 square roots of 3. 4. Now what to do? I would highly suggest don't write square root of 9, because it would be square root of 9. But square root of 9 reduces to 3. So if you do square root of 3 times square root of 3, just write 3. Square root of 5 times square root of 5, just write 5. Square root of x times square root of x, just write, as long as x is positive. Remember that? That was one of those little subtle things. We're assuming that variables are positive for a little bit. So this should be 4 times 3. Not 4 times square root of 3, just 4 times a regular old natural number 3. All right, and then let's see, that's first. Let's do distribution. So 2 square roots of 3 times square root of 5
is 2 square root of 15.
positive 2 square roots of 15. And then inner, or distribution. Negative square root of 5 times 2 square roots of 3.
Negative 2 square root of negative 15.
Negative 2 square roots of 15. And then negative square root of 5 times positive square root of 5. They do not cancel. You're
Which
not
one?
adding them.
So it's
Negative
5.
square root of 5 times a positive square root of 5.
Negative 5.
It's going to be negative
5.
5. Because square root of 5 times square root of 5 is 5, and negative times a positive is negative. Can I combine anything?
Yes.
Yeah, the middle two terms. What happens to them?
They cancel.
They cancel. 4 times 3 is?
12.
12 minus 5 is?
7.
What's cool here is 2 square root of 3 minus square root of 5 is an irrational number, and so is the other one. And when I multiply this irrational times this other irrational, it comes out to be rational. Actually, a whole number in this case, but it definitely comes out to be a rational number. What time is it? Oh, we got time. Where are you all going? Oh, you have to go. You have to go too? Are you going with her?
No.
I'll take the homework on there too. Even though I usually don't.
Okay.
All right, so those are conjugates.
Excuse me, sir.
Yep.
How did that first term come out to be? Yeah.
Here?
Yeah.
When you do square root of 3 times square root of 3, that becomes square root of 9, but I'd rather you not write square root of 9. I'd just rather you write 3. So the habit I want you to get used to is if you see something like this, the only thing you should write down is
Right.
just a 7. Don't even worry about the radical part. It's just 7. You got the two missing pieces together, and you came up with a new piece.
I blinked.
You blinked. That's all right. Don't blink. I go fast. 5 over the square root of 2. Now remember, when I was talking about radicals last week, there was a few rules. You could not divide by a radical because it has an infinite decimal place, and you can't move over the decimal place enough times to accommodate it. So what we have to do here is what's considered rationalizing the denominator. To change the denominator into a rational, usually whole number, or integer. Can be positive or negative. Now, we're going to use some techniques. We want to get rid of the square root of the 2 in the bottom. So what I'm going to do is multiply it by what it's missing. What's missing? Another square root of 2, because I know that if I multiply a square root by itself, it just kind of pops out. So if I multiply the bottom by the missing factor of the square root of 2, you got to do the same thing to the top. Why?
I don't know.
Just because someone taught you. Great.
No, because it cancels out, right?
Ah, and cancel is
Inverse to
inverse and identity.
identity.
Because square root of 2 over square root of 2 is equal to, and 1 times 5 over square root of 2 is the same thing, 5 over square root of 2. So I'm not changing the value of this fraction, I'm just changing the way it looks. So if I simplify this, it becomes 5 square roots of 2 over 2. Yay! Isn't this easy?
Hopefully you're not going to put those properties, like define them on the test, are you? You won't ask us to define the properties on.
Always, all semester long, or you're going to get sick of it. All right, most people get that one. What worries me is this one. The same idea that worked for 5 over the square root of 2 should work for 5 over the cube root of 2. Same idea, not the same thing. They're a little bit different. The reason that I multiplied square root of 2 on the top is because it gave me 2 factors of 2, and I can pop it out as a single factor of 2. This one is requiring how many factors of 2? 3, but I only have 1 factor here. So I have to introduce 2 factors of 2. So when I multiply top and bottom here, I'm going to write it a little weird. I'm going to introduce 2 factors of 2. Because when I multiply these two together, then I have how many 2's? 3 of them. And how many 2's do I need is 3 because of the index. So now that I have 3 factors of 3, the bottom number just comes out to be 2. But then you have to multiply the top. So what am I really multiplying by here? 4. So this is the cube root of 4. So 5 times the cube root of 4 is 5 cube roots of 4 over 2. Most people don't like that one. I don't know why, because it's the same idea. This one requires 2 factors before it can pop out. This one requires 3 factors before it can pop out.
Because it seems like you really can't do that. That's why.
Why can't you do it?
It seems as if you.
This divided by this is equal to 1, and 1 times something is itself. I'm not changing anything. The value of it is not changing, just the way it looks. It's the same idea. Let me do it one more time, uglier. But for some reason, people don't like that one. I don't know why. For example, 7 over the 5th root of 8. 7 over the 5th root of 8. How many factors do I have?
5.
No, that's how many I need. How many do I have?
Oh, you have one.
No, you have 8, 4.
I have not 4.
3.
3. I have 3. 2 times 2 times 2. 8 is 2 times 2 times 2, or 2 cubed. So I have 3 factors of 2 already. How many do I need?
2 more.
I need 2 more, because I need a total of
5.
5. So I'm going to multiply top and bottom by the 2 more factors of 2. So the 5th root of, in the bottom, I'll write it as 2 times 2. But at the top, I'm going to write it as the 5th root of 4. So this becomes 7 5th root of 4 over 2. Because I have my required 5 factors of 2. It's a little crazy. You don't usually see it. It's just a mental exercise. All right, how about something like this? 7 over 5 minus 3 square roots of 2. You can't divide by a radical. And I have a radical or irrational number sitting in the bottom. So how do I rationalize the denominator? I need a conjugate. Multiplying it by square root of 2, top and bottom, is not going to work, because it'll get rid of it in the second term, but it'll introduce it to the first term. So here, when you have a binomial, you got to do the conjugate. What's the conjugate of 5 minus 3 square roots of 2? 5 plus 3 square roots of 2. Whatever you do to the bottom, you better do identical to the top. I have seen people conjugate twice. In other words, they change it from minus to plus, and then plus 2, and that makes things wrong, because then this isn't 1 anymore. This has to be 1. All right, and then I just need to multiply it together. 7 times 5 is 35, plus 21, don't forget the square root of 2, over 5 times 5 is 25. 5 times 3 square roots of 2, 15 square roots of 2. Inner,
It's 15.
negative 15 square root of 2. And then finally, nope. It's negative 3 times positive 3.
Which is negative 9.
Negative 9. Square roots of 2 times square roots of 2.
Which is 2.
2. Just plain old
2.
2. Square root times the square root of itself is just itself. Alright, and then simplify. You know you did it right when these two inverse identity themselves away. Cancel. And then what you're left with on the top is 35 plus 21 square roots of 2. You can't do anything with that. Over 25 minus 18. 25 minus 18.
Which is 7.
7. I'm never good with multi. Ooh, nice one. I didn't plan on this.
You can cancel the.
Oh, be careful when you cancel here. If you cancel the first ones, you also have to cancel or reduce. I would rather you say the word reduce. What property allows you to do that? I'm doing it to both of them.
Yeah.
Wow,
Distributive. Remember what I said about the 7 in the bottom? You can write it as 1/7 times 35 plus 21 square roots of 2. That's the distributive property. So 35 divided by 7 is 5. 21 divided by 7 is 3 square roots of 2. So I have to ask you a question since we're running out of time. A little bit of time. What if you had something like 21 minus 18 square root of 5 divided by maybe I should make it 24 divided by Yeah, 10. I don't want them to all go into each other evenly.
Don't they?
If you have this, you can't leave it.
You can reduce it.
You have to reduce it, but it has to be every single number. So there's a couple ways of doing it. You could separate it to be 24 tenths, 18 tenths, square root of 5. Or you can factor out the common factor in the top and then reduce just the numbers. Most people don't do that. So what's common between 24 and 10? What's the common factor between 24 and 10? 2. 2 goes into 24? 12. What's the common factor between 18 and 10? 2. Now, you have to look at the whole thing. What's common between all three numbers? You can't do one different than the other. They have to be identical. So if this was, I don't know, 20, then 10 would go into 20 twice, but 10 only goes into 24 using a factor of 2.
You still use 2.
So you'd use 2 all the way across. So 18 becomes 9, square roots of 5, divided by 5. And you'll get the idea. All right, so that is rationalizing. I think that's everything. Oh, no, there's other things, but we'll cover that next class. It's a small little side topic that we have to deal with. So, homework. I'll write it down on the board. You already did the checkpoints for P3, or tried to, so if you haven't finished them, you should be able to do all the way up to checkpoint 9. I haven't gotten any further than checkpoint 9. We'll get to the end of this eventually. There's a lot of little things in radicals. So P3 exercises. Are going to be on page 46. 1 through 53 odd. 1 through 53 odd. And then P4 checkpoints. P4 checkpoints. Yep. So P3 CPs up to, what did I say, 9?
Yeah.
And then P4 CPs all. Oh, and I just made a mess of my form.